Hi, it's Professor Dickerson with part 5 in the multiple regression series. You don't need to adjust your computer screen. My hair is purple now. In this lesson, we'll be learning about something called dummy variables and how to incorporate them into our multiple regression models. So a dummy or indicator variable is a way that we can incorporate a categorical predictor into our model. So for a categorical variable, we'll need as many dummy variables as our categories minus 1. So we'll be starting with a simple example today where we're going to use sex as a predictor variable. So we have males and females, k equals 2. Thus, we'll only need 2 minus 1 equals 1 dummy variable. All right, this data set is a new one. It's called FEV. So FEV stands for forced exhalation volume. So imagine taking the deepest breath that you could and then exhaling as much air as possible. What would be the volume of that air? So this trait was studied in a large group of Boston teenagers during the 1970s, and we have lots of measurements taken on them. Let's go to jump. All right, so the response variable we're predicting is the FEV measured in liters. We have available to us a couple numeric variables, the teenager's age and their height. We also have 2 categorical variables. The group, whether they're a non-smoker or a smoker. Back in the 70s, there were a lot more smokers than there are now. And also the sex, so female or male. So we'll start by incorporating the sex as a dummy variable here. So imagine this is an on-off switch. If the switch is off, it's going to be set to one group. If the switch is on, it's going to be set to the other group. So to have the switch off, which we call the baseline group, we're going to assign members of that category a 0. So here, next to the females in the next column over, I've assigned all the females 0s. The males get a 1. So imagine our switch is on for them. They have a 1. And this pattern holds for the entire data set. So let's fit a model where we look at both a numeric and a categorical predictor. So how about height as x1? So that's measured in inches, it's numeric. And then x2 will be our dummy variable representing the sex. So like we said, kind of arbitrarily, we picked, we have to pick one. So how about females are the 0s and males are the 1s? Now, mathematically, what's going to happen if x2 equals 0? If we put a 0 here, anything times 0 is 0. So that term in the model would disappear. Whereas if we have a male, it's going to show up as a 1. So anything times 1 is itself. So therefore, this B2 is going to show up for males, but not show up for females. And that might shed some light on why we call the females here the baseline then. We're going to come up with some baseline prediction for females. And then if it's a male, we're either going to add or subtract some constant to adjust for the sex. All right, so to get this to work nicely in JUMP and have it make a helpful graph for us, we're going to change the coding of the dummy variable to an ordinal variable with the green. So if you forgot how to do that, you just go to your list of variables off to the left and right-click on the icon next to sex dummy. I'm going to change that to ordinal. All right, let's fit our model. So we want to predict the FEV, the response, and we're going to do that based on height and also the sex dummy variable, which is now ordinal. So let's run that. So we get some output that looks a lot different from previous multiple regression output. Namely, we have a scatter plot here with 2 lines on it, 2 parallel lines. And the legend says this gray line is the line of fit for sex dummy 0. So that is, we have a gray line representing the relationship between height and FEV for the females. In red is the other group, the ones which we coded as 1s. So that's the males in red. So they've got a separate regression line linking height and FEV. Their line seems to be sitting higher. All right, so think about, what do these two lines have in common and what makes them different, in the Algebra 1 sense? Well, they're parallel, so they've got the same slope. And actually, as it stands now, we forced them to have the same slope. Once we get to video number 6, we'll be allowing for the fact that maybe they deserve separate slopes. But for now, they have the same slope. It's just that the line for the males is some constant amount above the line for the females. So the y-intercept for the equation would be higher for the males than for the females. All right, let's have a look at our residual by predicted plot to make sure there's no funky patterns, no funnel shapes, no curves. So we do have one little bit of pattern here, which is that there's a cluster off to the left and a cluster off to the right. We will investigate that a little bit more in a second. Let's keep going down though. So our R squared is decent. It's not the highest ever, but it's not really low either. So we're explaining 58.8% of the variability in FEV. And after adjustment, that only goes down to 58.1%. So they're very close. So I'm not concerned about too many predictors in this model. Our root mean square error tells us that our typical prediction is off by about 0.515 liters. So that gives you a frame of reference, if we think that's a good prediction or not based on how much the lungs can hold. And our F-test tells us that, yes, at least something in this model is useful at predicting the FEV. So this is a model worth pursuing. We look down at our parameter estimates table for those t-tests. So is height a significant predictor of FEV? Looks like it is. We've got a high t ratio and a small p-value. The t ratio and the estimate are positive, so this looks like a positive relationship between height and FEV. Taller teenagers tend to have higher FEVs. We've also got a significant t-test for the sex variable. So the p-value there is also quite small. So we've found a significant difference then between the FEVs of males and females, even when we adjust for differences in height. Okay, because if we only looked at male versus female, we wouldn't know if it's due to some real biological difference between the sexes, hormones, etc., or is it just purely because males tend to be taller? So here we've teased those apart a little bit. We can now say that even adjusting for height, we've found a significant difference between the sexes. All right, so we can construct a prediction expression much like the other first order models that we've seen by using these estimates here. Okay, so we have two predictors in this model. We always have an intercept, so that's first. So the baseline intercept is the negative 3.255 if we round. Then we have a coefficient for height. That'll work the same as other coefficients we've seen for numeric predictors. But then here's our on-off switch. We've got to match up. Is it a female or is it a male? So if it's, this is how we set up the baseline. So remember, the baseline is always the group that got the zeros. So if it's a female, they get 0. Because remember, when x equals 0, this whole term is going to disappear. Right? So if it's a match to a female, we don't add anything extra. But how much would we add for the males? We're going to add this amount. because if x1, or pardon me, x2 equals 1, this will show up, and the amount it's going to show up is this estimate here for the dummy variable. So we'll add an extra 0.65 if it's a match for a male. All right, so let's practice using this type of expression to make some predictions. So if it's a female who's 66 inches tall, what would we predict for her FEV? Well, according to our prediction expression, the predicted value of y, FEV, would be negative 3.255 plus 0.097 times the height, which is 66. And then you don't really have to show this next part, but just to emphasize, since it's a female, we're adding 0. So there's no extra amount there. Okay, so just punch that in your calculator. And for this female who's 66 inches tall, we'd expect a FEV of 3.147 liters. Now, good idea if we have the graph just to check that that seems plausible. So I'm looking at 66 inches tall, and we're going up to the gray line because it's a female, and then going over. So we expect something in the low 3s, and that's what we got. Now for the males, the first part of the expression is going to look the same. Start with that kind of general intercept that applies to everyone. Add in the term for the height. But this time, since it's a male, we'll be adding in the extra constant of 0.65. All right, so if you put that in your calculator, you get 3.797. And again, measured in units for the response variable, which is liters. All right, so that would be, if we're at 66 inches, we go up to the red line and over. So upper 3s, eyeballing it, more specifically 3.797 liters. So hopefully it's become obvious that, well, what's the difference between the two? You know, holding height constant, the difference in the FEVs that are predicted is 0.65. So that's the distance between these parallel lines. Since they're parallel, it's going to be the same distance throughout the graph. All right. And just like in simple linear regression, because that's what we've really got here, we've got two simple linear regressions, one for males, one for females. We can calculate our error or residual by comparing the actual y to the predicted y. So if we're told, okay, there's this guy, he's 66 inches tall, and his FEV really is 2.276, what's the error associated with the prediction there? So we'd take the actual value. This guy actually exists, so you could look him up in the data table if you're curious. And then we'll compare to the prediction from the previous step, because that prediction was for a 66-inch tall male, and that's what we've got. All right, so it looks like this guy is going to have a negative error, negative 1.521. And we're still measuring that in the units for y, which is liters. Okay. Now let's do a little bit of data visualization. So you might be wondering, okay, we fit these two lines, but how well really do the males line up with the male line and the females line up with the female line? So let's go back to jump and see how we can color code. Now, you may have done this for your project, but in case you didn't, here's a quick lesson. So say we want to color code the males and the females. I can use this red triangle above my row ID numbers and go down to color or mark by column. So it doesn't really matter because it's a one-to-one correspondence. We could pick either sex or the sex dummy variable. And well, actually, we should pick the sex dummy variable because that's the one we put in our model. So with that highlighted, we can right click over here on these colored dots and choose the colors that we want. Now, I already saw that jump fit a gray line to the females. So how about for the zeros, I'm going to right click, pick colors, and make it gray so that it matches. And then we know that there was a red line fit to the males, so let's just match that and pick a red there. You could use, pink and blue or some other sexist combination of colors if you like, but this is what I'm using just to match those lines. Now, and it's nice because I just changed the colors now, but it's actually going to retroactively apply to the model that I already fit. We can see the separation between the males and the females. So it does look like, as our model suggested, the points for the females in gray tend to be on the lower end of things, and the points for the males in red tend to be higher. Now, if only the red dots were showing, think about where would you put the line of best fit. And if you're like me and you kind of looking at the pattern, I actually think that for the males, they probably deserve a steeper line. After all, we've got them kind of veering up over on the right-hand side of the graph. So maybe something like this would be better for them. However, just due to the model we fit, it's going to force them to be parallel lines. So if those two groups really do deserve separate slopes, it's got to kind of split the difference here. Right? If that bothers you, then good news, in video number 6, we can fit two lines with different slopes. All right, let's have a look at our residual by predicted plot. And now it should be abundantly clear why we have these two clusters. We have a cluster on the left for the females and a cluster on the right mostly for the males. And there's a couple in between that intermingle, but it's mostly separated here. So if you see that, now it is a pattern, but it's a pattern that our model accounts for. We have a term that's set up to handle that separation. So it's okay that it's not a total random scatter here. We're still looking that there's no curved patterns, and we're still looking that the spread up and down is similar across the graph. So it's okay that there's a little gap in between, because it looks like, at least to the first approximation, the spread up and down for the females' residuals is on par with the spread up and down for the males. Right. If we had more time, I would, go check for normality, independence, etc. But this plot looks good. Okay. So let me show you a quick and easy way to create a dummy variable. Because after all, you wouldn't want to have to go down every single row punching in 0 or 1 as appropriate. So this is quite easy to do. You're going to highlight the column that you want to recode. So say now we're interested in if whether the teenagers are smokers or not affects how much air they can exhale. So I'm going to highlight the group for smokers, or smokers versus non-smokers, and go up to columns and then down to recode. So highlight the column you want, columns, recode. So on the left, it's going to show you how many non-smokers you've got. So there's 74, 43 smokers, so a lot, but at least it's under half. And then on the right, we get to assign the new values. So, maybe this technique will come in handy for you for something else. These could be new words that you call them, like, people who do not smoke. You could just call them something else. But in this case, we're going to recode them as, that on-off switch. So let's set non-smokers as 0. And then for smokers, we'll flip the switch. They get a 1. And then Jump is going to create a new column. So we just need to assign a name for that column, unless we just want it to be the old name with a 2 after it. Let's call it Smoker Dummy. And then press Recode to implement. All right, now you can check this if you're skeptical, but every non-smoker should be lined up with a 0, and every smoker should be lined up with a 1. I'm going to go ahead and on the left, right-click on that new column and change it to ordinal. That way, Jump will give me the graph with the 2 parallel lines on it. All right, so one more thing. Let's now we already have color representing male versus female. Let's use the shape of the markers. So instead of just all dots, let's use different shapes to represent whether someone is a smoker or not. All right, so we did this a second ago. I'm going to use my red triangle above the rows and say row editor, or sorry, color or mark by column. So now I'm going to pick smoker. I'm going to turn colors off for smoker because I want to keep the colors representing sex, which we already assigned. But for markers, I'm going to give them some designation. So there's lots of options, but I'm just going to pick, I'll be boring for once, and pick the standard marker. So here's our legend. Now the zeros, or the non-smokers, are going to be represented with little empty circles. And the smokers, or number 1s, get plus signs. I'll press OK. And the labels then are over here. So empty circle is a female who doesn't smoke. Red circle is a male who doesn't smoke. Gray plus is a female who does. And red plus is a male who does. All right, let's fit a model using that new dummy variable. So analyze fit model. So we'll add the smoker dummy, and let's keep using height also. We saw that it was a good predictor in the last model. And we will predict the FEV still. All right, so our plot is a little busy. We've got the 2 different colors, we've got the 2 different symbols. But now, if there was a strong pattern where maybe the pluses were way above the empty dots or way below, something like that, we'd have a chance of seeing it here. But, so now we have 2 new parallel lines. These 2 parallel lines are really close to one another. So they're close in value. They're not that different. The gray line is the zeros, which remember was the non-smokers. So the non-smokers seem to have slightly higher FEVs here than the smokers who have been fit to the red line. Okay, just remember it's fitting those lines now, though, not based on the color of the dots, but on the shape. Where are those positioned? All right. Our residual by predicted plot doesn't show any strong differences in variance across the plot. Maybe it's a little narrower on the left than the right. We're not going to end up keeping this model for very long anyway. So go down. So the model as a whole is useful. At least one of the predictors is a significant predictor of FEV. Height is still significant, and in fact, even more strongly so than it was in the last test. It only shows p-values to 1 in 10,000, but our t-ratio is actually larger than it was before. The smoker variable, though, is not statistically significant. And if you had wanted to do a one-tailed test, smoking is bad for you, so perhaps, smoking would lower the ability to exhale lots of air from your lungs. Well, your p-value would be half of this, so about 0.082, still would not be statistically significant at the 5% significance level. All right. So hopefully that makes sense, that we saw the lines were a lot closer together, so there was less of a difference between these two groups than there were between the two sexes. The estimate there for the smoker dummy was negative. So let's just make sure we're clear what that tells us. So remember, this is a more complicated model here. We'll get there in a sec. So think of the 0 and the 1 as our on-off switch. So the baseline, kind of just height versus FEV for non-smokers, we'd have the intercept of about -7 plus about 0.16 times the height. But when it comes to the smokers, they're also going to get a little bit extra added on. It's just that now, what are they going to have added on? It's a negative number. So there was a slight negative effect of smoking on the FEV. Right? So we see that on the graph because the red line for the smokers is a little bit below the gray line for the non-smokers. How much below? This amount, the negative 0.15. All right, lastly, let's try putting all three predictors in: the height, the sex, and the smoking or not. I guess we're not using age, but we've got a good model going. All right, now, although smoking wasn't statistically significant in the last model, remember, things can change as we add or subtract predictors. So it's worth giving it a try again here. Now, when I've got two dummy variables in there, the model is a lot more complicated than it was in the previous version. So we don't get, a graph with parallel lines anymore. So that's gone. It's all in our minds now. But we can still test which predictors were significant. All right, so our ANOVA says that this is a useful model. At least one predictor in there is a good predictor of FEV. So in this landscape, with these particular models, these particular predictors in this model, it looks like height and sex are still very good predictors of FEV, but smoker is even less useful here. Perhaps because there's a relationship between which sex is more likely to smoke, or, if taller kids are more likely to smoke because they're older than the younger teenagers. So some of that difference in smoking may have been accounted for already by those other predictors. Okay, so the R-square will always go up as you add more predictors. So if you absolutely needed the best prediction of FEV, you might keep smoker in there. It does help, although it wasn't significant in this run, because I can see that the R-squared and the adjusted R-squared are still pretty close. If we saw a big drop off, that would indicate that, hey, you really should get rid of something. So let's compare the two best models that we saw today to predict FEV. So one was just using height and sex. So both of those were significant predictors. And then the most recent one was height, sex, and whether or not someone is a smoker. So comparing, the one on the right does have a higher R squared because it's got more predictors. That's always going to happen. R squared will never go down. Worst case, it's going to stay the same, but it almost always goes up. When we adjust, though, and account for how many predictors are there, notice it's almost a tie. 0.581 on the left, 0.5817, which I guess would round to 0.582. So, higher would be better, but we've matched the first two decimal places, so it's really a trivial difference at this point. All right, the root mean square error. So remember, we want this to be small. This is showing the typical error in our estimates. So on the left, 0.515. On the right, 0.5146, which would round to 0.515. So again, it's almost a tie. So probably here, given that we have pretty much the same predictive ability for both models, we would favor the one on the left because it's simpler. It's also more plausible to think about, holding height constant to check the difference between the sexes, or holding sex constant to check for differences among the heights. Okay, so now you should be comfortable using dummy variables to represent a categorical variable with two levels. In the next video, we'll consider what we'll have to do to incorporate 3 or more levels.